Yes.
Yes.
Yes, we can hear.
Okay. So today I'm going to cover the GLM function, like which is mainly we use we have talked about that one in class about logic regression. So the first one is like as we just we have seen before, like you use the question mark plus the GLM as how to upload the like how to load the uh, how and description for the GLM function. So in general, it's fitting the generalized linear model, and then you have several options to use that one. Like you can choose the family, formula, data, all those stuff. And then I'm going to show specific examples today about like how to use GLM function and then how to produce results and compare the predict. Okay. So the first thing is there are several things I would like to say before. So this line, this function is just simply like you to remove all the working environment and then the variables here. And then the set seed function, you will see this one below, which is just set the seed. And then every time when you generate the random numbers or random functions, random variables, all those things are going to be based on the seed, the number, the value of the seed. So it can help you to produce same results as when you try to reproduce like regenerate the numerical random variables below. So I'm going to mention this later. So first thing is about to load the package. So today I'm going to use the package psych, which is a package for psychology techniques, and then also the library based on the Woodridge. So this one, so the Woodridge package includes all the data for the Woodridge textbook, which is the introduction to econometrics. I know like a lot of you have seen that one before, but this one is just a data set. So here, this will be the documentation for package Woodridge. And then you can see there is several data sets here. So one we are going to use today, we are going to use the Apple data sets. So this will be the description for the data data sets, and then it contains 17 variables, includes ID, education, date, states, this price, other things. So I'm going to show first the so let's see what does the data here. Let's first check the data here. So this is the data when we have so this each ID represents for a household, and then it includes the education, how many years you're in school, and then the date, also the state, and this one price. This one represents for the regular Apple price, and this one represents for the eco labeled Apple price. And then this one is in season if H size represents household size, and then male equals to 1 if it's male, it's dummy variable. So there are several variables here. And then this one represents for the regular apples, like how many apples does one family how many apples does one household buy, like in pounds. So this is the regular pounds for regular apples, and this one is the pounds for the eco labeled apples. And then so today we are going to predict whether the household will buy some eco labeled apples or they will buy some regular apples. And then we are going to use the logic regression to predict if the household will buy some eco labeled apples in this case. Okay. Any questions so far regarding data sets and descriptions?
It's not about the data sets and the description. Are you recording this for the future reference?
I'm sorry? What do you mean? Am I recording this one? Well,
I think he was asking if you were recording the lecture, the Zoom call.
I'm not sure if I can record this one.
Because I was trying to find the lab section for the previous lab section on the Zoom, but I couldn't find it. So I was just curious about, are you recording this any chance for the future reference or anything?
I'm not sure because like when the professor do the lecture, it record automatically. It's that one. He says the seminar time from 5:30 to 7:30, but I'm not sure how to do this one. The labs. Let me see. Actually, I'm not sure how to do this one. I think I'll figure out maybe next week. So let's continue on the stuff I'm going to cover today. So the first thing is when we try to predict if the household will buy some eco-label apples, we are going to first generate two dummy variables. So this one, as numerical function takes when in the data sets, when the eco-label is bigger than 1, which means the household at least buys some eco-label apples, then it generates the numerical as what. So you can see this by eco variable. So it's the dummy variable when it equals to 1 when the household buys some eco-label apples. And similar for the buy variables, this is also dummy variable. And then I'm going to assign I'm going to combine these two. You can use this function or you can use the cbind function. They are going to do the same thing, but just to like add these two features to the data sets. You can see here, it contains two additional columns, which shows the two dummies. And then we are going to predict if the household will buy some eco-label apples here. And so first thing after we have the data sets, the first thing we're going to do is we're going to check the summary statistics, which you will do that every time when you try to play with some data sets. So the first thing is about the dimension. So this data set contains 660 observations of 19 variables. So it's 660 times 19 660 by 19 matrix. And then we check the name for the apple for the data sets, which contains 19 names. This will be the names for each features in the data sets. And then also the summary for the apple, which gives you so you can see the minimum, the first quantile, median, mean, third quantile, and the maximum number for each variable for each feature inside the data set. And then this describe function is really helpful when you do some analysis. So this function actually this one belongs to the psych library. So that's why we load the psych library here. And then this one gave you the description for each features. Give you the number of observations, mean, standard deviation, median, trim, mean, max, and also something like kurtosis, skewness, all those stuff. So make sure you do understand each of the function, and then what does it represents, like each, like the skewness, the kurtosis, if it's the skewness roughly represents if it's skewed more to the negative or to the positive given the normal distribution. And the kurtosis represents if it has a long tail or short tail at both sides. Make sure you do understand these things before you do the analysis. And here will be the logistic regression. So logistic regression is a statistical model which use a. So this logic regression is a statistical model that uses the logistic function to model a binary dependent variable. The model's probability of a certain class or event existing, such as pass and fail, win or lose, live or dead, or like healthy or sick. So today, here we are going to try to talk about predict if we only given these data sets and we want to predict given the features of one household, is it going to buy the eco labels? I mean, is it going to buy eco label apples or not? So that will be why we use the logistic functions today. I mean, logistic regression today. Okay. So this attach function just attach the data to the R database, which we can use. So like as we can see before we attach the Apple data sets, every time when we try to call some variables inside the data sets, we're going to use Apple and then get the dollar. Sorry. And then so get the dollar sign and then get the add education here. And after we attach the Apple data sets to the searching area, you can just call this one directly. So that's why it's just help you to simplify the coding. So GLM function, which will be this line. This is the GLM, how we use the GLM function to do the logistic regression. So it's called GLM, and then we give the dependent variable at the beginning, and then we have all the independent variable, which will be the features that we are going interested in, like the education, age, and family income, male, if it's dummy variable, male or female, and then regular price for the Apple, eco label price the price of eco labeled Apple. And then this one, the family equals to binomial, which this one defines the logistic regression. So if it changes to something like Gaussian, then this one should give you the same results as the last function. So this function decides. So this function decides if it's logistic regression or other things, and then you can check about like other. So when you do family here, so you can see there are different kind of distribution you can assume, like the binomial, Gaussian, gamma, and then Poisson, other things. Okay. So let's run this regression first. So after we run the regression, we have assigned the regression to this log I here. And then so we can check how many items are going to. So you can see, let's first check this variable. So it contains 30 variables here. It contains coefficients, residual, fitted value, effects, R, rank, all those features. This regression. And then the main results we are going to get is we can use the summary function to call the summary for this regression. So here will be the coefficients here, and then this is the standard error, and then this Z value represents roughly T stats here, because we are interested in the T stats and if those coefficients are significant. And so after that, we can simply call the function coefficient log I to get the coefficient value for the estimate variables. And then you can also call the summary log I, and then with the call the coefficient here. So it will only show the summary for the coefficients. Okay. And then so in order to show the why this one, so let's do this. So in order to show if the after we do this calculation, which is the first column divided by second column, in general it will be this the first column here divided by the second column here. So this one will give you the value exactly equal to the Z value here. So you can compare this one. So you can see this one is 0.6 0.609. This one is 0.609. So it just show you another way to calculate the t-stats here. So this is roughly the logistic regression. And then, so how we use R to predict based on the logistic regression, we have already, like the estimated results we have already gotten. So we use the predict function here to predict the probability that the household will buy eco-label apples. And the tag response option tells R to output probability of the form P, like y equals to 1 given x. And this one is, so let's first do this one, the predicted probability, and then we can check the head of this one. So this one, the tag response gives you the conditional probability for y equals to 1, which means when y equals to 1, which means the household actually buys some eco-label apples in that case. And then this head function just let you check the beginning value of this variable, 6, and then you can change the number here. And then we assign another variable here, the log predict, which so we first assign a variable with all zeros, and the length equals to the length of the bi-equal variable here. So in order to make a prediction as to whether the household will buy eco labels, we convert this predicted probability into dummy labels 1 or 0, which means so all the, as you can see, so when you check this result, you can see all these numbers are like now integers. So we want to convert these like numbers into integers, either 0 or 1. So 1 represents for the household will buy some eco-label apples, and 0 represents it will buy nothing. And then so we generate this function when log I dot PR, this one is bigger than 0.5, then it will equals to 1. So let's check this variable. As you can see here, so for the first one, this one is 0.81, it's bigger than 0.5, so this one equals to 1 here. And then as the fourth one, this one is smaller than 0.5, so this one equals to 0. That's how we convert the probability into a dummy variable. And then you can also check the mean for the this dummy variable. This means like about like 73.6% of the household will buy eco-label apples based on prediction. And then we can also check the mean of the actual number for the household. Like they're only like 62.4% of the household will buy the eco-label apples. So here it generates. So next step we want to compare like how many errors, how large the error we got in this case based on the logistic regression. So we use table logi.predict and then by eco. So this one is just create a table because both of these variables are dummy variables. So it only contains number values 0 or 1. So when the actual, so this horizontal one, and like the column represents like how many of the apples, how many households are actually buy eco-label apples, how many of those are not buy. And then this so when this one equal to 0, when the prediction equal to 0, this one is the actual number equal to 0. So these are the correct predictions, and this one is also predictions as well. So on the diagonal of this matrix, it represents like total there is like 442 households out of 660 like who got like right predictions here. And then this number just represents when the prediction give you like the household shouldn't buy any eco-label apples. but actually they are buying some. So this is number like when we gave the correct prediction. And this one is the same thing, similar stuff. The prediction gave you like 146 households. They should buy some equal apples, but actually they don't. So all of the numbers on the diagonal table, this means like how the correct prediction inside the data sets. Okay. And then gave you so this one, the logic predict equal to by echo. This one, the mean of this one gave you like actually how much how many households they gave the correct prediction. So here it gives you like 66.9% of households are correctly predicted. And you can also do this prediction. So you can also check this one, like we use 442 divided by 60. It gave you this exactly same number as this mean. Okay. So any questions so far?
Are you gonna upload the markdown file on Canvas later?
I'm going to upload the PDF file here because like when I upload the format may be changed.
Okay, cool.
So you get all these. So this one, like the R markdown file is more like a script, and then this one give you all the explanation. You can see the results, and then yeah. So this one is much more neat than the.
Yeah, I just like want to like run the code myself sometimes. So like, if you could upload like 2 files, it could be great. Otherwise,
I mean, like I think it would be good practice if you can do that yourself, because you need to do the homework, and then it's better to give some practice, like you code yourself. Just follow the instructions.
Cool, gotcha.
And so like this one, the first part, this part is the in-sample predictions, because we here. So when we do the prediction here, it's an in-sample prediction, which we use the whole sample as the training data. And then so next step, we're going to use auto sample forecasting. So we train model only based on roughly 80% of the whole samples. So here it's just we set the seed to 1, 2, 3. This one is just give you a fixed seed, and then so okay. This is successive function is for a random number generation. Every time when you set the same seed, you will generate the same random numbers here. Otherwise, you cannot generate the exactly same number because it will randomly pick the seed is built inside the program, and then you cannot generate the same function. I mean, like same values. In this case, it's just you can set to whichever number you want, but just in order to get the same results as I got, you need to set the same value of the seed. And then we create the random variable, which is this RU form. This one is just the uniform distribution. So it generates the random numbers based on the uniform distribution. And then this one is how many of the random variable we are going to generate, and the mean is from 0. X is so this one is like more like the uniform distribution 0 and 1. So the minimum is 0, and then we randomly pick the length of these variables, and then from this uniform distribution. Okay. And then so we do the train here. So the train here is just simply a variable like with 660 observations. And then this one is generated as false at the beginning. And then for all the random variables smaller than for all the random variables are smaller than 0.8, we replace the value as true. So let's check the variable here. So you can see at the beginning all of these values are false, and then we replace the values, and then you can see there are roughly about 80% of the value are true. You can see it's 81.9% of this value are true, and then so it's roughly 80%. Because in general, like theoretically, when we talk about like randomly pick numbers from the uniform distribution, it should follow the uniform distribution. But in general, I mean, like when we randomly do the generate the values, it will be roughly about around 80%, and maybe like smaller, like 97% or 81%. All of these are acceptable. Okay. So here we detach the whole Apple data sets, and then we attach the Apple sets with the train. So let's check this one. Describe. Here you can see that the observation is actually 541. So when the value like equals to true, it will it represents the train here. It will only return the value like equals to true. So we got only like 541%, roughly 82% of 660 observations. And then we assign the test sets as Apple not true. So when we do this one, so do the not true, they will reverse the values here. So you can see the last value of the train at the beginning is true, and then this one returns true false if we get the not true sign here. Okay. So we assign the test sets as Apple when so not in the train data sets. So roughly we separate the data sets into two subsets. One contains the training data, one contains the testing data. So this part is training, this part is testing data. And then this is how we do the output sample forecasting. Okay. Any questions so far? Okay. So let's first do the Ols regression. We use the LM function, which we have introduced before. And then, so the reason we use the LM function is just, I would like you guys to have a directly comparison between the logistic function and then the Ols regression. Okay. So we do this one, do the Ols regression first, and then we summarize the Ols regression, which we got these results. And then similar as before. So this prediction function, when we want to do the out of sample prediction, you would like to put the train data sets at the beginning and then put the testing sets at the second one. So this one will predict the value predicted by eco dummy variable in the test sets based on the features we have already do the regressions. Okay. So we do the prediction, we summarize the prediction, and you can also do describe. And this one OS represents for out of sample, just in case. So you can see it's 119 observations here. And then we do the OS predict, like do the same conversions we have done before. For all the values bigger than 0.5, we convert those as 1. And then we compare the prediction with the actual data. So similar as before, we have 40 plus 55 correct predictions. So 95 predictions, correct predictions as total, and then 24 false predictions. And this mean function is also just checked like we got like 97% 79% correct predictions here. And so next step, we're going to do the logistic regression here. And so follow the same step, we do the logistic regression, we get a sample summary, and then we do the predict based on test sets. And then we do the summary. So all of these things follow the same step as we have done before. And then you should get a result here. Okay. So like here, the logistic regression here, it gives you 37 plus 58 correct predictions. And that's total like 95 correct predictions as well. So let's compare to this one. It's not the same results when I generate the PDF. Wow. So like when I do in my own computer, it gave you like 83.8 correct predictions, but here it gave you 85%, 79% correct predictions. This is just because the version of R, it may have changed a little bit, and then there's little things like changing for each version. So it's enormous stuff. Okay. So let's I will use this example to talk about like the Ols regression. So this one, when we first do the Ols out of sample prediction, we got like 82.3 correct predictions. And then this one, the logistic one, roughly give you 83.8 correct predictions. So in general case, theoretically, logistic regression should give you a better estimation when we do something like even predict the probability rather than so this one should generate better results here, better than the Ols. But still, so you can see like it still give you the same thing, roughly the same results in a different version of the R. And then so in my case, this one correct Ols failed to predict 24 observations, and the logistic regression fails to predict 22 observations. So that's why we will use Ols regression as an initial as a benchmark. So we do roughly all the time we will do the Ols regression at the beginning, and then do some calibrations based on the data. We want to do logistic regression, or you may want to use like other regression method just to get a more accurate results here. And then also you can check this star. There is like 3 star represents for the significant level at 0, and then this dot 1 represents significant level at 0.05 significant level here. So and you can also do that one. So these are based on both the t-value and the. So you all know how to convert t stats to p-values, right? So this one is just based on the t-value. You can use t-stats or use the p-value to do the when you estimate the data or the model. Okay. And question? Okay. So I do recommend you to change the family, change the binomial to Gaussian, or change different kind of distributions, and to check the results. So based on different family, it will change to different kind of results and give you different predictions. And then when we change to Gaussian, this one should give you this one should give you the same results as the Ols regression. Yeah. Let's see. Okay. So roughly it give you the same percentage, 79 point. So this one 40, 16, 8, 55 is exactly the same as the Ols regression. So given different kind of family, we will get different results. And after later in this class, you may use like Ridge, LASSO regression, all those stuff. And those are much more, they're much better when we're dealing with larger data sets. Like when we have maybe hundreds of, like thousands of observations and hundreds of variables here. Okay. So any questions so far? Okay. So that's all I'm going to cover today. And then let me know if you have any questions. And I will upload the PDF later on Canvas.
Is there another problem set due anytime soon?
I'm not sure. I mean, like the professor will give you the questions, and so I'm not assigning the assignments, but I will ask him.
Okay, thanks. So because like I mentioned before, like this one is the first time we do the online class, so all the things haven't been settled. And then what I would expect you guys to learn is like something like the convex stuff we covered today, and then all those like basic derivations, like how you do something, how you explain bias and variance trade-off, which one give you better methodologies, and then like all the things like related to the lecture and then related to the homework, you should be familiar with those stuff. And so he definitely will ask you a lot of things like we have mentioned before, like the Newton method. He won't ask you about like specific derivations because that might be too hard. But like when you do ask to do simple derivations, like to take the partial derivative or prove, or like it may ask you to prove which one is convex, which one is concave. So all those things are reasonable here, I think. And we haven't talked about the exam stuff here. And then, so the professor is still learning how to teach online, like how to control the time and then do the lecture online. So once we have settled down those stuff, I will post an announcement on Canvas. Yeah. Other questions? Okay. So if you don't have any question, I'm going to end today's meeting, and I'm going to upload the PDF on Canvas, and I will try to figure out how to recording next time.